Um, Hi everybody, I'm Moreno. I work in the CRC in Paris with Sarah Zohar and Emmanuel Comet. First of all, thank you very much to the organizer to invite me, and thank you, Barbara, for giving me the possibility to be here today. And I will talk about incorporating pharmacokinetic information in phase 1 study in small population. And I'm a member of the INSPIRE project. INSPIRE is innovative methodology for small population research, and the focus is on development of novel methods for the design and analysis of clinical trial in rare disease of small population. The project coordinator is Nigel Stallard, and as the ideal project, it is founded by the FP7, and we are divided in 4 work packages, the one led by Sarah Zohar, then the second by Nigel, the third by Martin Posch, and last by Tim Fried. As you can see, I work in the first work package with, of course, Sarah Zohar is the leader, Emmanuel, that is the deputy leader, Corinne Alberti, Frederica Lenz, Nigel, Tim, and of course me, I'm a postdoc. And our aim is to develop a novel methodology for improving dose finding in early phase clinical trial by incorporating data on pharmacokinetic and pharmacodynamics. And in our first year, our aim was to propose to study and compare methods that use PK measure in dose finding design, and we want to know how to include that information, as how we can incorporate PK as covariate, dependent variable, any other way. So we work in phase 1, as I said, dose finding, and our objective is to estimate the maximum tolerated dose, the MTD. We have discrete and fixed dose level, binary criteria, so toxicity yes, no, and very small sample size. For that, usually we use adaptive design and Bayesian adaptive design, as I will explain later. And for the first year, we studied and compared dose finding method that use PK measure as covariate or dependent variable. So first of all, we had to find existing approach that usually they are built for a specific case. Then we modify and adjust them in order to compare them, to apply them on the same clinical setting, and so to be able to compare them, their performance. So let's start with find the existing approach. The idea of the introducing PK data in dose escalation study is not new, but is rarely used in practice. And the first paper that I found was the paper of Colling et al., where they suggest to use preclinical data to select the dose that you will use in an up and down design or in a 3+3 design, so algorithm design. Then Piantadosi and Liu, where they use a parametric dose response function with also PK measure of the exposure as covariate and not only the dose. Then Patterson et al. Is Patterson and Whitehead that use Bayesian hierarchical structure, and Quigley et al. That is more a bridging study because they want to find a dose that which is associated with a mean PK response. Is a bridging because they went for adult data to children data. And then I saw in 2011 a presentation of Barbara on dose selection incorporating PK-PD information, and they use the entire model, so not only the UC or the Cmax. Then we decide to what to apply, what to modify, and we decide to focus on a method that include AUC as covariate and dependent variable, so not yet the entire model. That will be the next step of our work. And the first method that we found in literature in that case is the Piantadosi and Liu method. It is an extension of the continuous reassessment method, where we have a parametric dose response function we have as a covariate both the dose and something that depends on the PK. Delta AUC means the difference between the AUC estimated of the population and AUC of the patient. And here in the blackboard you can see my modification in order to then apply all the method on the same clinical setting. And I put the logarithm of the dose because I found that often this relationship is linear in the logarithm scale and not in dot scale, and then adjust also the last term in order to have the same scale. Then for the prior, because I said we are in a Bayesian secting, so we use prior for estimating a parameter. I kept the same prior suggested by the paper. And for the dose allocation rule, since we are in adaptive design, that means that we have to choose the next dose to give to the next patient that enter in the study on the basis of all the previous information that we have of the previous patient. So we say that we will give the dose which posterior probability of toxicity is nearer to our target probability, theta. The target probability is something that you decide before starting the clinical trial and is the toxicity that you can accept. Then the second method is the method of Patterson et al. They use a Bayesian hierarchical structure with a mixed effective model for analyze PK data. So here you can see the model with the logarithm of the AUC that depend on the dose, and then the random effects and the hierarchical structure. Why they have also the random effects? Because they work in a crossover study with healthy volunteers. And for the dose allocation rule, they had two different dose allocation rules. The first was the highest dose satisfying a constraint, and the second was the optimality on the posterior of theta. For our modification, I drop out the random effects since we don't have a crossover study, but we have only one data for one patient. And then I changed the prior or nu, since in that case nu is linked to the inter-individual variability of clearance, and we expect it between 0 and 1, so beta would be a good choice. Then for the dose allocation rule, before defining them, we need not only to define theta, our target probability, but also an L, that is a fixed threshold, that because we say that the next dose will be the one which the probability that AUC will exceed that threshold is near to our target probability. We didn't use the optimality in that case because we have a linear model, so we choose in between the first and the last dose, so it was not so ethical, how to say.
Just do you have your keys to your unit? A set was left in the door.
Number 9.
You might miss it.
Okay. And I call that method PK-lim in our modification. Then there was the method proposed by Whitehead et al. And there was still Patterson. So it is a modification of the previous model where they take care about PK, PD, and incidence of adverse events at the same time. So we have three models, the one of logarithm of the AUC versus dose as the previous slide, then the pulse rate depending on the AUC, and then the probability of toxicity versus AUC, the logarithm of AUC. Again, we are in a crossover study, and for our modification that we will call PK log, we drop out the PD equation because we were looking only on PD, only on PK, and I put PK-lim, the model before, with the last equation, and I changed priors in order to have the same prior of the other method that I compared. So I put the uniform prior like in PK-cov, and for the dose allocation rule, the idea is similar because we say that the next dose will be the one which probability of toxicity, the posterior probability of toxicity, is nearer to a target probability. How to compute that? It is expected value because we have the probability of toxicity given by that formula, and then from the PK-lim we have also the probability to have that AUC given the dose. Then I added two modifications. The first was to couple the pk-lim method, the one with the L, with the CRM, since, as I said before, CRM pk-lim depend on the threshold that you decide before starting the trial. So in that way, if you choose proper L, pk-lim could be a second safety threshold on the AUC and CRM on the dose. Then in pk-pop is pk-log, so is that one, where here instead of putting the logarithm of the AUC of the patient, I put the logarithm of the AUC of the population predicted by pk-lim. In that way, we have it is a way to pass from the population level, from the patient level to the population level, because here, when we are at that level, we are more or less at the patient level because we take care about the UC of the patient, and then we want to go to the dose here, so at population level. Then we had to find a clinical setting, and after a meeting with Giulia Lestini and François Mentre in Paris, we decided to use the paper of Evelina et al. On defining a therapeutic window for the novel TGF-beta inhibitor, that number, based on the pharmacokinetic and pharmacodynamic model. The TGF signaling has been recognized as an important regulator of tumor growth, and inhibiting it is a novel approach. And in the paper, they simulate from preclinical data to predict the dose range for a human clinical trial. And here we can see the picture that they put in the paper, where the blue line is regarding the percentage of inhibition, so the PD, and on the black line is the median of the UC predicted, of the human UC predicted from preclinical data, and they choose the window with the two constraints related to the preclinical data. And then they did the clinical the trial and estimate then PK/PD after, and they use a first order absorption linear two compartmental model for PK and an indirect model for related plasma concentration and peace mode data. And for our model, we took only the PK equation, and we use only a one compartmental model and non two compartmental model, like in the paper of Giulia Lestini, and we use the same mean value proposed in the paper of Lestini. And for the inter-individual variability, we decide, as in the paper, not to put inter-individual variability in Ka, but only in clearance and volume of distribution. And we use two different values in order to see how they behave. And in the plot, you can see the concentration versus time of the 6 doses that we use in our used in our simulation. Then also for each patient, order that variability, we add also an error, a proportional error of the 20%. Then last step, we link PK to the toxicity, and we assume that the HIF patients show toxicity if that linear function of the UC is equal or greater than a threshold tau t. And with alpha I belong from a log normal distribution. Putting everything together, so the one compartmental model and that threshold, we achieved that probability of toxicity versus dose. And on that plot, you can see how the probability of toxicity change versus dose if we increase omega alpha. So in that way, we increase omega alpha. And in that plot, you can see how, without omega alpha, how the probability of toxicity change if we increase the tau t, the threshold of toxicity. Then we simulate 7 different scenarios. The first was our core scenario, since we use the tau t suggested from the paper of Evelina and the inter-individual variability of the paper of Lestini. And then we decide to change the parameter in order to see how the results change. And for the trial setting, we use 30 patients per trial, cohort of 1,000 simulation per scenario. We add no skipping rule to all the dose finding method, so we don't skip those during the dose allocation. And all the methods are applied after we show the first toxicity. And we use 10 sampling points for the AUC estimation to put in dose finding model method. Then we compare them, and in our core scenario with that value from the tau t omega alpha inter-individual variability of clearance and volume, we have that curve for probability of toxicity versus dose. The black point are our dose level, and the red line is our target probability of toxicity of 0.2, so only 20%. So the MTD, the maximum tolerated dose, is the dose level 4. And we apply all the method, and as you can see, I use CRM-PK with different L because I want to know how it behaves if we have an L below the real threshold or higher than the real threshold. And we can see that, for example, PK log has the worst performance if we don't take care about the CRM-PK with the very wrong L, because our L is below the real threshold. And then if we have the real threshold here, so if we are very lucky, we are God, we can decide before to choose the right L, we can reduce the underdosing, the overdosing. Then in the scenario 4, when we add variability in omega alpha, we have that other curve for probability of toxicity versus dose, and the MTD is dose level 2. And we can say that PK curve, the first method, hesitates between the two doses nearer to the MTD, and also PK pop is hesitate in two doses, and CRM PK with a proper L could have very good results. Then when in that scenario we reduce the inter-individual variability of clearance and volume, and now the MTD is the dose level 5. And we can see that, of course, if we have CRM-PK with lower L, we cannot achieve any good results, but we can achieve good results with the good L. Here you can see that the last two have more or less the same behavior, since when L is higher, CRM-PK tends to be only the CRM alone. And then the last scenario where we put in less inter-individual variability, but variability in omega alpha. Then we checked about the distribution of doses, because each method gives us a different distribution of doses for the patient. So this is the number of doses, patients allocated to each doses, and to each dose, and we can see different distribution. But when we try to estimate PK parameter with monoliths, we didn't found any big result. I know there is a table with many numbers. Trust me, they are more or less all the same, so we cannot see any big difference, despite the distribution, the different distribution of doses. Then also in scenario 4, when we add variability in omega alpha, and in scenario 6, where we reduce the variability of omega CL, of the clearance. And as you can see here, the last are similar, because I say to you the the CRM PK tends to be only the CRM when L is higher than the real L. So for summarize, I look for the percentage of MTD selection and estimation of PK parameter, and we say that including only PK measures of exposure like the AUC or similar to this Cmax, it doesn't increase the percentage of the right MTD selection. And for example, PK curve has the problem that you need to choose the right beta 0, and it is similar to the logic of P versus logarithm of dose, and this is also similar to PK pop, so they are more or less they behave very similar. And PK log could be a very good model, but not when you have the relationship between toxicity and AUC is an EV side function. So as we put a threshold, we have an EV side function, and here we don't have an EV side but a logit function. So it's difficult to approximate a logit function with an EV side if you don't know it. And the serum MPK depend on the threshold L. So I heard one time Franz Maitre talk about the difference between dose finder and dose estimator, and dose finder take care only of the discrete number of doses. So you can after your model you cannot extrapolate data because you take care only about that doses. Instead, the dose estimator want to estimate the entire curve. So after you can extrapolate on the window, of course. And serum PK, I think this could be in the middle. And for the future work, we want to move in phase 1-2, including efficacy, binary and continuous. So the both. And then we want to include the PK PD estimation during the escalation, so the full model based, like the talk that I saw on the web. And we will also work on the prior distribution because we want to combine data from different sources. Then I want to say thank you to my group, because we work together, for the Inspire that pay my salary, to Giulia Lestini of DD and Franz Maitre of both DD and IDEA project, and Evelina that was very kind when I saw her and she helped me with advice. Thank you very much.
Questions to Moreno?
I just suggesting for extensions to your work, because actually I was the person I was working with Scott and John Whitehead years ago. It's not so much the MTD that you're interested in as well. Most pharmacokinetic curves you imagine follows an S.
Mm-hmm.
And you don't care about being at the top of the S. If you start being on the S, you come back down. So actually, same principle with the MTD, they've got a finite, if they've got 30 people, they'll use all 30 people. So if they get to the MTD or they get to the top of the S, they try and characterize the what they call the linear part of the curve. So an extension to your thing is actually when you get to dose 5 and you reach the MTD, spend those patients coming back down the curve and to get the model better estimated. Because that's the only part of the curve that they're interested in. So they want to characterize that as good as possible. So an extension to your work is actually once you reach the thing, to spend those patients coming back down and get as good an estimate as possible.
This could be the next, because we don't want only to go on overdosing, because for ethical problem, from mathematical point of view, I want to do it, but I don't think that.
It's just actually that using those patients as good as possible. If you got 30, then use all 30 if you can.
Thank you.
So, are you just using the last doses for your selection?
Sorry?
Are you using the last dose that you used in the experiment to select the MTD?
Mm-hmm.
So why aren't you using all the data to do some kind of estimate of the MTD? Why just use the last dose? It's only 1 point.
No, to choose.
The question is whether you're using only the last point to make your selection.
No, the last point, we analyze after each patient, we took all the data that we have before, we analyze the model, and then from the model
That's to select your next dose. But when you're finished, you have data on all, data and responses, and you're not using any your response data. In the end.
We use again all the points, we estimate the curve, and we take the one with probability of toxicity near what we want.
But then it should be,
It's not.
the estimator should be somehow between this, or this MTD dose should be
Can you speak
between
up a little
those.
bit?
I cannot hear, sorry.
Then if you use your models, then your estimator of, or estimate of your MTD should be, with probability close to 1, to be between doses, discrete doses. Or you use as an estimator only those doses which coincide with administered dose.
What if the estimator
Sergey,
is
you can
between two
translate.
adjacent doses?
What is that?
What if the estimator is between two adjacent doses at the end? What do you do?
I think
In
you
our
have
scenario-
the rules somewhere on the slide.
Yes, there is the here to hesitate in between two doses. We need that value is perfectly equal to do two doses, and computationally speaking, is the probability is zero.
That's your allocation rule. Not
At the end,
Yes, but the MTD is the same.
Data. So it's using all the
Think
data.
about it.
But
He's
he's
not
working.
using all the data.
Why not? He's using all the data to fit again the model and calculates the estimate of the next dose, and that's final experiment. That's the dose.
But why don't we get to see what the data actually looks like in terms of the responses?
What response? He's doing
The
one toxicity.
probability of toxicity.
Yes.
It's in there with the data hats.
Yeah,
all
yeah.
the hats, based on all the
Is the
data.
posterior.
That's not part of the results you get to see.
Yeah, here it's two problems are actually mixed up.
Yeah.
One is allocation and another
It's
dose
estimation.
estimation.
Yeah.
And dose estimation here method chosen is the simplest one, which actually can allow only doses which are administered. Period.
Correct.
So it's use all data, but estimator for dose is not the best one,
Yeah.
from my point of view.
Well, he's claiming that this is an appropriate hybrid of the two philosophies.
And actually, I have. Okay, so Sergey.
Oh,
okay.
But speak up, please.
Okay. Then I will block a view of speaker. So,
Louder.
okay, I will. So do I understand correctly? So if you administer some dose D,
Yeah.
and you know how you administer twice a day, once a day, then you can get, at least with some approximation, your PK curve.
Hmm.
And now you say, okay, and it's unique solution, as I understood. Okay, so now, what you suggest, or somebody suggests, I didn't really realize who suggested it, you say, okay, I introduce as a covariate dose D, and then I introduce as additional covariate area under the curve. Yeah?
Yeah.
But area under the curve is uniquely defined by the dose. So what is the sense of introducing this
Is
dose
But that's
in this
Piantadosis.
AUC?
Yeah, it's what I think the first time that I read the paper. Then since it's the delta AUC, and if you use only linear compartmental model, if you do the calculation with the AUC of the population minus the AUC of the patient, the mean value is 0, and the variability doesn't depend of the dose. So they are
It's only
correlated.
what? You know dose very well. And AUC you have to measure again. And it's uniquely defined by, let's assume you can measure AUC exactly, so no observational
Mhm.
error. Okay? So then it's completely defined by dose D. Completely,
Yes, but in that way,
uniquely.
they put the variability of the AUC. The
But it's
variability.
only make picture worse. Because instead of you measured, you know those, let's assume exactly. So you can define AUC precisely, so with zero error.
Yeah, yeah.
And then you replace this AUC with something which you observed with some measurement error. Why not to do instead of that, I have D and I add, you say, okay, it's not linear dependence upon D, then I add, say, D squared.
I think it's because how it's used operationally. I mean, the no effect limits are usually written in terms of kineticists drive these studies. It's pharmacokineticists who actually are usually making the decision. And the no effect limits are usually written in terms of AUC. And what people usually want to know is what dose will give you the toxic AUC. So it's wrong in a way in that they're rewriting an equation where AUC is outcome, but what they want to know is what dose will give you the toxic AUC. That's why AUC suddenly goes on the wrong side, because they're trying to predict the future. They're always trying to say, given their model, what dose will give you the toxic AUC in the future. Now you could argue it's the wrong way around to do it, but that's how the kineticists work. So you're looking at any kineticists in the room. But yeah, usually it's because AUC is what they're interested in.
I think another thing is that AUC reflects population variability. It's not just measurement error there. So if it's a mixed model, the AUC will depend on the parameters of the model, and then if we assume that the parameters are random because of the random variation in the population, then you have it shown through the AUC.
So you want to say that all population variability coming through this AUC?
I don't know if all, but some.
Well,
Okay, let's.
for some model you can write
Okay.
down the formula for AUC
That
for
is
all
good
the
explanation.
parameters.
Thank you, thank you. Thank you.
Yes, Franz.
Yeah, just a small question. I'm surprised that you are surprised that the choice of dose will influence the PK parameters. Why do you think it will influence it? The monolix results, you say they're all the same, but
Yeah.
you should expect that they're all the same, no? Why would you expect that sort of distribution of dose later on?
Yeah.
Why did you expect any change?
Because for the
Here,
distribution
yes,
of
for instance, this
for the
one.
distribution
Why
of
do you
those,
think that it will affect the estimation of the PK parameters?
because we have different dose allocations. So for example, here
Yes,
we have
but-
more, but then we have also 10 points. So it's not
I
so.
can't hear the answer.
But
That since we have
shouldn't be,
also
because dose, it's proportional to dose. So how is your error? Is additive error constructed?
proportional.
Not surprised.
It's a linear PK model.
Yeah, it's a linear PK model, so those are not. So whatever, as long as you have the same number of observations, and it won't affect a lot.
Did you?
I have a question.
Yeah.
So in this adaptive trial, you take samples, blood samples in the simulation, I gather.
Yeah.
So did you consider how? Did you do it in some systematic way, or did you
Yeah,
optimize them?
No, we use 10 points, 6 in near the peak, and then on the tail without optimize it. Then for the estimation, I tried with non-compartmental analysis in order to not put any model. But I found that if I want to put it in a loop, I need a method to take care about the tail of the distribution of the non-compartmental analysis. I failed in doing it, and then we use a nonlinear least square with a one-compartmental model to estimate PK parameter of the patient, but without at this stage without optimal sample points of the design.
Any other questions? Maybe the last question. Anyone?
What do you mean by last?
Well, we can continue the discussion during the break, but because it's time now to have a break, let's thank the speakers.